In this presentation, we will discuss the control of multiple quadcopters to map building fire hotspots. Quadcopters are small, typically unmanned aircraft propelled by 4 rotors. Because of their versatility, quadcopters have been used in a variety of applications. In particular, they are well suited to aiding in monitoring of forest wildfires. A small fleet of quadcopters can cover a large area and take pictures of key hotspots to better understand the evolution of a fire. Applying this same approach to urban firefighting on a much smaller scale introduces a number of challenges, including tight maneuvering and obstacle avoidance. Our team has developed a novel hybrid control strategy for autonomous fire monitoring of a burning building. Our controller has 3 levels. First, we use the A-star algorithm to map a rough trajectory of waypoints for each quadcopter to hit the desired targets. Then, we use a model predictive controller to generate dynamically feasible trajectories between the waypoints. And finally, we use a nonlinear classic controller to track the trajectories. We simulate our controller with a simple rectangular building with 6 target points mapped by 2 quadcopters. The dynamics of quadcopters are complex and highly nonlinear. We use a state space model with 12 states for each quadcopter. First, the position of the quadcopter relative to a fixed reference frame defined by x, y, and z. Second, the linear velocity of the quadcopter in the same reference frame. Third, the orientation of the quadcopter in space defined by the roll, pitch, and yaw angles. And finally, the angular velocity relative to the body reference frame. The inputs to the system are the thrust generated in each of the 4 rotors, which are used to calculate the total applied thrust and applied torque. This model includes gravity, drag, and inertial effects, but neglects more complex aerodynamic phenomena such as rotor deformation.
As the first part of our project, we need to extract waypoints that get our drones to the desired target points and feed them back to our MPC controller for further processing. To do so, we need to first formulate our first step as a search problem. The A-star search algorithm in this case is our best option. A-star was created as part of the Shaky project back in 1968 in Stanford University. It is essentially a heuristic search algorithm that finds the closest path from start to finish. It combines uniform cost search and greedy search. To ensure its optimality, it uses a function known as the heuristic function to evaluate the cost of each possible path. The priority of nodes orders by the heuristic function Fn equal to Gn plus Hn, where Gn represents the path cost or backward cost, and Hn represents the goal proximity or forward cost. Here for implementation, we use Python's priority queue data structure, which allows us to quickly and efficiently select the lowest cost partial plan from our queue of all partial plans. For the heuristic function, we use Euclidean distance that ensure it's admissible and consistent. For environment setup, we use a voxel map, also known as 3D grids, because A-star is designed for the structural environment. Our voxel map is basically a map constructed by cubes that has dimensions equal to 1 meter. We use a 3D array to represent the map, with values between true or false to represent its occupancy. The graphical representation is shown below. For our testing purpose, we design a scene where there is a building with a dimension of 15 meters times 15 meters times 20 meters, which is the length, width, and height. And the target points are spread across the surface of the building. The starting points for Zone 1 and Zone 2 are 10 meters away in front of the building and 2 meters away from each other. The illustration is shown on the right.
To generate trajectories between waypoints, we use a model predictive controller. The cost function of the MPC weighs 3 attributes. First, the difference between the desired and actual states of the quadcopter at time n. Second, the deviations of the quadcopter from a direct straight line path between waypoints. And third, the magnitude of the inputs. This helps to generate trajectories that are direct and efficient while still ensuring dynamic feasibility. An additional dual variable lambda is introduced to prevent collisions between the quadcopter and the building, which is defined as a polytope given by the matrix A and the vector B. The formulation we use ensures that the quadcopter will always remain a distance d away from the building at all times.
The reference trajectory obtained from the MPC is discrete, can contain discontinuities, and is of reduced order. So not all motor inputs can be obtained from the MPC, and the reference trajectory need not be dynamically feasible. However, we can construct a smooth trajectory for tracking as follows. First, a low-pass filter is used to smoothen out the discontinuities in the reference trajectory. Then, polynomial interpolation is used to obtain a continuous trajectory. The position and yaw angle references are sufficient to obtain all the states of the quadrotor and as well as the motor inputs. Finally, we use a nonlinear tracking control to follow the reference trajectory. The advantages of this method are as follows. Guarantee of convergence under some assumptions like bounded velocities. The ability to track aggressive maneuvers with large angular and position variations. Exponential stability for tracking. Complete rejection of matched disturbances. And small computational expense. As you can see from the results of our simulation, the controller manages to keep the position error low even with different initial conditions and in the presence of unmatched disturbances.
We tested our control on a simplified building model with 6 randomly selected surface points on fire. The way we implement our control is by first finding feasible trajectories using A-star and MPC in real time without disturbances, and then we use the non-linear tracking controller to track them with random disturbances. And this is our simulation result. As you can see, our controller is able to find the trajectory and track it with almost no error, even under disturbances. Our quadcopters are able to map all the target points while avoiding each other and the obstacle.